Right. Hello, everyone. So this is the recording for chapter 11, lecture 1. So we will be spending 3 lectures on this chapter. Um, it's continuing on basically from chapter 10 with more bonding theory. So as you guys already learned in chapter 10, we learned Lewis theory, right? And that's our first bonding theory. That's the simplest. And it's one of the most useful ones. But after a while, this bonding theory, Lewis theory can break down. And so we need to introduce, more theories to explain other things. So chapter 11 is going to involve 3 bonding theories. You guys are going to first learn the VSEPR theory, which will tell you molecular shapes. And then we'll go into valence bond theory, which will tell you what orbitals are involved in bonding. And then we will go to MO theory as the very last thing. So today we will cover VSEPR theory. It stands for valence shell electron pair repulsion theory. It sounds really complicated, but it's actually really intuitive and easy. It's the theory that's going to allow you to think, what do these compounds look like in 3D, right? Now that's where Lewis theory breaks down, because Lewis theory is only for us to represent molecules on 2-dimensional paper, right? And we really can't tell from Lewis theory what these things look like in 3D. So we have to bring in VSEPR theory, and it works in conjunction with Lewis theory, right? But we can now bring in a new theory to help us figure out what the shapes of these molecules are. So in order to do that, all you need to remember is that electrons don't like each other, right? Because they're all negatively charged, and like charges repel each other. So when you place electron groups around the central atom, they're going to be most stable when they are as far apart from each other as possible, right? And this was kind of like what I was telling you guys already in one of the steps for the Lewis theory, is to put the surrounding atoms evenly around the central atom, right? Because again, they don't like each other. So, hopefully you guys are getting into the habit of already doing that, which will help you with shapes now, right? Um, so first, let's talk about what electron groups are. So electron groups are defined as anything. Lone pairs are considered electron groups. Even a single bond is an electron group. Is a double bond is also one electron group. A triple bond is also one electron group. So everything is easy. It's just considered as one electron group. So in this picture, right, what it's um, illustrating to you is that if you were to put 3 electron groups around a central atom, and here's the central atom, okay, what is the way in which you can do it so that you maximize their distance, right, from each other? Because they are going to repel each other, right? So you would correctly probably guess like a triangular shape, right? The way I like to think about it, right, is like, how far you can put the electron groups as far away from each other as possible to minimize electron repulsion, right? Now, even if you try to force these 3 electron groups to be close to each other, they would just, as soon as you let go, right, they'll just immediately repel each other until they come to an equilibrium. Uh, and that equilibrium is going to be this triangle, right? Because what they're trying to do is minimize repulsion. And so that's actually the basis of the theory. It's this electron-electron repulsion that is what gives rise to the shape of molecules, right? And so in this case, with the 3 electron group, you can see that it's triangular, but the technical term for it is called trigonoplanar, right? Trigonal meaning 3, right? Um, legs, right? Trigonal. And then planar means it's flat, right? All of them lie in the same plane, these 3 balls, okay? So yeah, we're gonna do this exercise, and I have molecular models here that is going to help us visualize these shapes in 3D. So I would recommend, if you guys have a little bit of money to spare, it's not that expensive, that you buy one of these. So you can do it on Amazon. It's called the inorganic or organic model set. I have the teacher one. You don't have to buy that one. You just buy the regular one. I think it's like $15 or something like that. But I think it would be extremely helpful for you, especially if you know that you're going to be continuing studying chemistry, or biochem, or more science classes, because you'll see this again. Okay. All right. So let's go back. Let's go to the board now. And I've made a table, right, in which we're going to do this exercise where we're going to see, okay, how do the electron groups affect the shapes of molecules? Okay. So you may want to do that too. You may want to pause the video and make this table and just go along with me. I think that'll be, the best for your learning as we do this together. Okay. And just as a reminder, right, how to count electron groups. Okay. A single bond is still considered one electron group. A double bond still considered one electron group. Triple bond, one electron group. Lone pair, one electron group. So everything gets counted as one, right? Because it's a group. Right? It's like a group of one, a group of two, a group of three, but it's still only one group. Okay. So let's get to it. We're gonna start with the lowest number of electron groups. So first column, I'm gonna put 2. Okay. BP stands for bonding pairs. LP stands for lone pair. Okay. EG stands for electron group. Okay. So I want you guys to think about it while I put this together. See if you can correctly guess. If I have 2 electron groups, 2 things, how should I put them around a central atom so that they're as far away from each other as possible? Okay. And you would say this, right? So here's the central atom. I have 2 things. How do I put them as far away from each other as possible? It's got to be opposite each other, right? You can imagine that we can't do better, right? So that's it. And that gives rise to a certain shape, doesn't it? Gives rise to linear, right? Okay. So let's fill out our chart here. We have bonding pairs, 2. There are no lone pairs here, 0. And so your electron group geometry is called linear. Okay. Like a line, right? The molecular shape, okay, is also linear, as you can see. So molecular shape, how that differs from electron group geometry is it ignores the lone pairs, but we don't have lone pairs here, right? So it's still looking like what shape? Linear. Okay. And then the bond angle, right? You guys know with bond angle of linear, it's gonna be 180. Okay. Now let's continue with our game. Okay, but now we're gonna step it up to 3 electron groups. Okay, think about it, guys. 3 electron groups. How can I put 3 things around a central atom so that they are as far away from each other as possible? Okay, so you should say this, right? Remember, we did this on the slide. Looks like a triangle, right? They're as far each other as possible. Okay, we call this trigonal. Do the 3 legs, planar. You see how it's flat on my hand, right? So trigonal planar. 3 bonding groups, 0 lone pairs. Trigonal. Okay, molecular shape. Oh, still trigonal. Okay, and then the bond angle. Okay, this is quite easy to figure out, right? Because the whole entire circle is 360 degrees. So divided by 3, 360 divided by 3 is 120. Okay. Now we're going to play a little game. I'm going to rip one of the bonding pair off. I'm going to replace it with a lone pair. So now it's going to look like that, right? Okay, so now I have still 3 electron groups, right? 1, 2, 3. Okay. 3 bonding pairs. Sorry, but now it's 2 bonding pairs. And I have a lone pair. So 1. what is my electron group geometry? Well, all three of them, right? All three electron groups is still in trigonal planar. Okay. But now my molecular shape, when we do molecular shape, right, we don't see electrons, they're invisible. Okay. And so what does this look like? Okay. Do you see that it's obviously not straight, right? So it's not linear. It's like a V shape. We call that bent. Okay. And then the bond angle for bent. This is how we should think about it. Because we've replaced one of the bonds with a lone pair, the lone pairs repel more than the bonding pairs. So now the electrons, these electrons in the lone pair lie closer to this atom, and it's repelling away these bonds more. So what it's doing is it's pushing these bonds away from it. So these bonds going to get squished. So this angle now is going to be under 120, right? It used to be 120, but these electrons push it further away. So now it's less than. And that's all you have to say. You don't have to specify a number. Okay. All right. That's it for 3. Let's step up to 4. So what do you guys think? If I have 4 electron groups, how should we put them so that they're as far away from each other as possible? It would look like this. Okay. So you guys can see that, right? And some people, they do a guess. They say cross, for 4. It's close, but actually you can get even further away than a cross, right? So it looks like this. This shape is called tetrahedral because these atoms form the vertices of a tetrahedron. Okay, so this shape is called tetrahedral. All right, so let's fill it out. We're up to 4. We have 4 bonding pairs, no lone pairs, tetrahedral. Okay, molecular shape is still tetrahedral. Okay. And the bond angle here, not obvious. Okay, so you're just gonna have to memorize it. It's 109.5 degrees. Okay. All right, so let's play our game. Okay, I'm gonna rip off one bonding pair. We are going to replace it with a lone pair, like that. Okay, so what is our, how many electron groups do we still have? 4, right? 1, 2, 3, 4. Okay, but now we have 3 bonding pairs and 1 lone pair. So for the electron group geometry, we still have tetrahedral, right? Okay, but for molecular shape, we don't see the electrons. So we'll cover that up. And what does that look like? It looks like a pyramid, doesn't it? So it's actually called trigonal pyramidal. Like a pyramid with 3 legs, right? Trigonal pyramidal. Okay. See, 3 legs, but it's a pyramid. Unlike trigonal planar, it had 3 legs, but it was flat, right? This one's not flat. Okay, so as far as the bond angle, again, we can do it like this. We can think about it like this. This lone pair here is going to squish these 3 bonds because it's pushing them further away. So it's gonna put, squish these angles so that it's less than 109.5, right? Just like with the trigonal bent, right? Before that we had. So it's gonna be less than 109.5. It's actually has a number. It squishes it down by about 2 degrees. So we'll call it 107 for trigonal pyramidal. Okay. All right. Let's continue to play our game. I'm gonna rip one of the bonding pairs off, replace it with a lone pair. Okay, so now we got this, right? 2 bonds, 2 lone pairs. Our electron groups, we still have 4, right? 1, 2, 3, 4. Okay. But now we're down to 2 bonds and 2 lone pairs, right? 2 bonds, 2 bonding pairs, 2 lone pairs. We're still at tetrahedral. Okay, right? Still a tetrahedral. But for molecular shape, we don't see the lone pairs. We only see the atoms and the bonds. That looks again like what? What shape's that? You guys have seen it before? Yeah, it's that. Okay. And now for the bond angle, these two lone pairs push even harder on these. So we had 107, and now it squishes it even more, down 2 more degrees to 105. Okay. Okay, so we're done with this game, right? For 4. Let's go to 5. Can you guys imagine what 5 would look like this? Kind of pretty, very symmetrical, like a star, right? So what you'll see is that there are 3 here that is in the plane, right? It's flat. And then there's a one that's above and one that's below the plane. So in a way, it actually looks very kind of like the Earth, right? Where this is the equator, and these are the axes. This is the axis, North Pole and South Pole. Okay. This shape is called trigonal because of these 3 in the middle, bipyramidal because there are 2 pyramids. You see, there's a pyramid up top, and then there's an upside down pyramid here, right? So trigonal bipyramidal. Okay. As for 5 bonding pairs, 0 lone pairs. We'll call it trigonal bipyramidal. And what is the molecular shape? Still trigonal bipyramidal. Okay. And then the bond angles. Let's see. Can you guys see that in the equatorial plane, it's 120, okay? And then between these two, it's a 90. See, it's perfect right angle here, okay? So we say 90 and 120. Okay. All right, so let's continue with our game. Okay, gonna rip off one of these bonds and replace it with a lone pair. Now, not all of these are the same. So you have to think about which one you rip off for 5 electron groups. You need to rip off one of the equatorial, okay? Because if you rip one of these off, right, these will just rearrange anyways because there's a lot of space up here. So think about just ripping off the equatorial ones and replacing it with a lone pair. Okay, so it looks like that now. We still have 5 electron groups, right? 4 bonding pairs and 1 lone pair. 5 electron groups, 4 bonding pairs, 1 lone pair. We still have, for the electron group geometry, trigonal bipyramidal. Okay, and then for the molecular shape, I'm going to cover up the electrons, right? Okay, so now what does that look like? Seesaw, right? Okay, so seesaw, let's think about the bond angles. The lone pair is going to go squish everybody down. So all you have to say is less than 90, less than 120 for seesaw. Okay, makes sense, right? Okay, let's keep playing our game. So again, we are going to keep ripping off the equatorial one. Okay, for trigonal bipyramidal, always rip off the equatorial one. And so now we have this. Okay, so I still have 5 electron groups. But now I got 3 bonding pairs and 2 lone pairs. Okay, I'm still trigonal bipyramidal. But now my shape is what? Let's cover up the lone pairs. And you look at just the bonds and the atoms. What letter of the alphabet is that? T. So it's T-shaped. Okay. And T-shaped is really easy for bond angles. See, these are all right angles, right? So it's 90. Okay, and you know these electron groups can squish this down, but since they're opposing each other, they kind of cancel it out. So for T shape, you can just say 90. Okay. All right. So that's it. Let's move to 6 now. Got 6 electron groups. What's that gonna look like? Again, like a star, but now we have 4 in the equatorial plane, right? And then we still have North Pole, South Pole, right? So this is 6 bonding pairs, 0 lone pair. We call this octahedral. Okay. Octahedral because these atoms form the vertices of an octahedron. Okay. Molecular shape is still octahedral. Okay. And the bond angle, as you can see, they're all 90, aren't they? Okay. All right, so now let's keep playing our game, right? Let's play our game. Rip one of these off. It doesn't matter which one, again, because it's all symmetrical. And replace with a lone pair. We still have 6 electron groups, but now it's 5 bonding pairs and 1 lone pair. So our electron group geometry, as we see everything, still octahedral. Okay. But we don't see, for molecular shape, we don't see the electrons. So we cover that up, and all we see is what? That looks like a pyramid, doesn't it? But the base is 4, okay? And what shape is the base? It's a square. So it's called square pyramidal. Square pyramidal. What is the bond angle? Well, this is going to push on this a little bit. So it's going to be a little bit less than 90, right? As you can see, because this is going to press downwards, okay? All right, let's keep playing our game. If we're gonna, which bonding pair are we gonna rip off? Wouldn't it make sense to do it here so it's symmetrical, right? And not here. So we're gonna rip this one off. And go to this. Okay, so we have that, right? So again, we still have 6. But now it's 4 and 2, right? 4 bonding pairs and 2 lone pairs. So we're still octahedral for electron group geometry, right? But for molecular shape, we don't see the lone pairs. So what does that look like? It looks like just a square, right? So we call that square planar. Square planar is exactly 90 because this repulsion, right? This pushing down this way and this one pushing up kind of cancels it. So we'll just say 90 degrees. Okay, so that's it for your shapes. That's all you need to go to. So, I mean, we can, you know, there are definitely molecules with 7 bonds, 8 bonds, 9 bonds. In my grad school, I actually worked with one that was 12, at 12 electron groups around it. So you can imagine the naming there was really interesting, right? But you guys don't need to go that far. You guys just need to know up to 6. So make sure that you know, you're not going to have this on the exam. So, you know, the best way to do it is just practice, right? And buy the models, and practice with the models. I can also lend you the models too, if you want to study with it, right? That's going to be really helpful. Now up to 4, you can kind of do with your fingers. So this is how I like to do tetrahedral, right? Right, does that kind of look tetrahedral, right? And then I just go, okay, what if I remove one? So now I have a lone pair, okay? One lone pair and 3 bonding pairs. What does that look like? Oh, that's trigonal pyramid, right? Now I remove another one, and what does that look like now? That looks like bent, right? So little tricks, but really, you know, you're just gonna have to practice and play with it. There are certain patterns that I can point out to help you guys see. Do you notice when it is that the electron group geometry and the molecular shape are exactly the same? This one you have 0 lone pair, right? So when you have 0 lone pair, you can see that. Yeah. It's the same, right? Electron group geometry and the molecular shape are the same when you have 0 lone pair. They start to be different when you have different pairs, right? And then what else do you notice? The electron group geometry for everything that has 3 electron groups is called trigonal planar, right? Everything with 4 electron groups has an electron group geometry of tetrahedral, right? That's the base geometry, right? The molecular shape is what you see as the overall shape, but the base geometry is the same. For 5, it's always trigonal, 5-pyramidal, okay? And for 6, it's always octahedral. All right, so let's go back to the slides. Okay, and so now that you guys know the shapes, right, we're going to start from the beginning with, a chemical formula. And we're going to ask, okay, what shape is this molecule? We give a chemical formula. What you need to do is first draw the Lewis structure, right? Then determine the number of electron groups around the central atom. You only care about the central atom, okay? Don't look at the surrounding atoms. The shape is all based on the central atom. So once you have your good Lewis structure, right, with all the steps and everything that you guys already know how to do, then look at the central atom and just count the number of electron groups. And remember, everything gets 1, right? A single bond is 1, a double bond is 1, a triple bond is 1, a lone pair is 1, okay? And then you classify what electron group that is, what is the molecular shape, what is the bond angle, right? Based on the table that we just did, okay? So let's go do one of the problems. Okay, determine the molecular geometry of NO3 minus. All right, so let's go to the board and do that. NO3 minus. Okay, first off, we should always start with a Lewis structure, right? So first step, total number of valence electron, 24. Okay, and now I'm doing this quite quick, right? Because you guys already know it. Nitrogen central atom, you got oxygens around. Single bonds, that's 6 electrons used. I got 18 electrons left. Okay. How am I going to put it? 3 lone pairs to the outside atoms. Okay. That's 18. Okay. And then I'm going to check for octet. Nitrogen doesn't have octet, right? So I'm going to move that down. We have N double bond O. O has 2 lone pairs. Right. We didn't touch the other oxygens. Okay. If you guys notice, remember, this is one of the examples where we can have resonance structures, right? So the double bond could be here. If I had chosen these 2 electrons, it could be here. For just determining the shape, you do not have to worry about drawing all resonance structure. Just come up with the best one, right? So here, everybody has octet. And check formal charge. Nitrogen has 1, 2, 3, 4 around it right now, but it should have 5. So it's missing 1, say plus, right? This oxygen, 1, 2, 3, 4, 5, 6, 7. It should have 6. It has an extra, so that's negative. This one's negative as well, because it looks like that one, right? This one, 1, 2, 3, 4, 5, 6. So this one is 0. Okay. If you add up all the formal charges, 0, minus, minus, and plus, you get a negative, which matches nitrate, right? Now, as far as formal charges, it's, there are 3 non-zero formal charges, which isn't great, but it really is the best that we can do. So you can just take a second to recognize that's the best we can do, right? To fulfill everybody's octet and also have the best formal charge. So this is our structure, or one of the resonance structures. Again, you don't need to draw all of them for determining shape. Okay. Once you have the best one, then what you do is you count just the central atom, right? You count how many electron groups there are. Double bond gets is one. Single bond is one. The other single bond is one. So for a total of three, right? So we got three electron groups. Well, I don't know why wow, balloons just came up. Interesting. On the screen. I don't know if you guys see that. But cool, whatever. So we got three electron groups. So I put a note to myself, right? Three electron groups. And then how many bonding groups do you see? Bonding pairs? All three, right? We got three bonding pairs. Zero lone pair. Okay. So, right, according to the table we made, three electron group geometry, we already know for three, right, is trigonal planar. Okay, and then also list the molecular shape. Molecular shape, since there's zero lone pair, is still trigonal. Okay, there we go. Okay, and usually I'll ask for the bond angle as well, right? And trigonal planar's bond angle, we already know, right? Triangle is 120. This bond angle is 120 degrees. Okay. So yeah, that's what you do, right? When you have from the beginning a chemical formula, do the Lewis structure first, then go to your electron groups, and then figure out what is the electron group geometry, molecular shape, and bonding. All right. Let's do another example. PCl3. Let's do that one. That one's on the slide as well. PCl3. That's 5 plus 3 times 7 is 26 electrons. Okay. Central atom, that's going to be your phosphorus. Spread the 3 chlorines around, so it's going to be this, this, and this. And single bonds first, so you go like that. That's 6 electrons used, 20 electrons left. There. And then you can have, now you put 3 lone pairs on each, right? Pairs to fulfill the octet for the chlorines. So how many dots have I made? 2, 4, 6. That's 18. I have 2 more electrons now. Remember, that's why I'm working inwards. I put it on the central atom, right? Okay. Everybody has octet, yes. Okay, but if I do formal charge right now, 1, 2, 3, 4, 5 for phosphorus. Phosphorus should have 5, so that's 0. Chlorine, 1, 2, 3, 4, 5, 6, 7. And chlorine should have 7, so that's 0 as well. Looking great for formal charge. We got octet and we got formal charge, right? So we're good. Now look at the central atom. It's all about the central atom. Look at the central atom. How many electron groups do we see? 1, 2, 3, 4. 4 electron groups. And how many bonding pairs? 3. 3 bonding pairs. And 1 lone pair. Okay. So our electron group geometry will be tetrahedral, right? Remember for 4, it's tetrahedral. Right, like that. That's tetrahedral. Right? And then, 3 bonding pairs. 3 bonding pairs, 1 lone pair. What does that look like? Pyramid, right? Trigonal pyramid. It's the molecular shape. Or more correctly, trigonal pyramidal as our molecular shape, and then our bond angle. Can say is 107, right? Remember, tetrahedral is 109.5, right? But then the lone pair squeezes it a little bit more, so it's a little bit less than 109.5, 107. Okay. All right. All right, one more example, ICl4 minus. ICO4 minus, so I, that's 7 plus 4 times 7, and the negative sign is a plus 1. Okay, so that's 28, 29 plus 7 is 36 valence electrons total. Obviously, iodine's bigger than chlorine, right? Iodine's below chlorine, so it's going to be the central atom. And you can put the chlorines around evenly. We'll do 1, 2, 3, 4 bonds. That's 8 electrons used. We got 28 electrons left. Okay. So 3 pairs on the outer atoms. Okay, that's 3, 6. That's 6 times 4. It's 24. So I have 4 electrons left, or 2 pairs, right? 2 pairs. I should put them on the central atom, right? That's why it says working from outer atoms to the inner atoms. So the last electrons get put on the central atom, right? So we got 2 lone pairs on there. Count the electron groups on the central atom now. 1, 2, 3, 4, 5, 6. That's 6 electron groups. Okay. 4 of them are bonding pairs. 2 of them are lone pairs. Okay. And 6 electron groups. Remember how you put it around the central atom, so it's as far away from each other as possible. It's called octahedral. Okay. And then with 2 lone pairs in molecular shape. Yeah, 2 lone pairs in molecular shape would be square planar. Right. And then bond angle. This angle here is 90. Yeah. All right. So yeah, just keep practicing those. Try to do it without the table, right? So I know right now you guys may be new to that, you're using the table, which is okay, but start to try to really imagine what these look like in your mind. Again, the models are going to help if they're in front of you to kind of imprint those shapes into your mind so that you can, be doing this in no time without looking. And it's, it's not going to feel like it's that hard. Right? Okay, let's go back to our slides. Did that. Okay. Now let's talk about polarity next. Oh, wait, multiple central atoms. Okay, so if you have larger compounds, okay, so now you have a big molecule like that, and let's say you're asked to do the molecular geometry and molecular shape for each central atom, right? How you would do it. You just redraw it with all of the bonds in the line. You basically draw the Lewis structure, okay? And then you make a table, right? What the atom is, okay? What is the electron group geometry? What is the molecular shape? And then what's the bonding? Okay, so the first central atom I see is nitrogen. You do it by one central atom at a time. Okay, it's not asking you for what is the shape of this overall molecule, or on the screen, right? What is the shape of this overall molecule? It looks like a poodle to me, right? But that's not what they're asking, right? They're asking like, what is this shape around each central atom? Okay, so first do nitrogen. And how many electron groups around nitrogen? 1, 2, 3, 4. So that's going to be tetrahedral for electron group geometry. Okay. And what's the molecular shape? Well, there's 1 lone pair. So you got tetrahedral, 1 lone pair. That's trigonal pyramidal. Okay. So that's the shape around just nitrogen, right? And that angle would be 107. Remember? Right. Then you move on. What's the next central atom? Carbon. Carbon. This carbon. Let's call that carbon number 1. This carbon number 2, because there are 2 carbons. Okay, so carbon number 1, 1, 2, 3, 4 electron groups, again, would be tetrahedral. But this time there's no lone pair, so shape is also tetrahedral. And tetrahedral is 109.5. Okay. Let's go to carbon number 2. Again, you can see that 3 electron groups, right? 1, 2, 3. Okay. So we're ignoring the other ones, right? We're only concentrated onto carbon number 2. So that's 3 electron groups. Trigonal planar. Okay. And there's no lone pair on C2, right? So shape is still trigonal planar. And for trigonal planar bond angle, it's 120. Okay. Next central atom would be the oxygen. Okay. So it's this oxygen, right? This oxygen we don't care. Remember, we do not care about the surrounding atoms. The shape and geometry is only dependent on the central atom. So this oxygen has how many electron groups? 1, 2, 2 bonds, and 2 lone pairs. That's 4, right? So it's tetrahedral. And since there are 2 lone pairs, okay, so 2 lone pairs means it's bent. And bent, tetrahedral is 109.5, right? Then it goes down to 107 trigonal pyramid. Now it'll go down to 105 for bent. Okay. So yeah, that's how you do it when you have a large molecule with multiple central atoms. Okay. All right, let's do another example. This one's on your slide too. Let's say we want to know what is the geometry for the central atoms of this molecule, CH3OH. Now, this is a larger molecule, like it has more atoms, right? It's certainly more atoms than you're used to when you're doing Lewis structure. So when you have larger molecules, the book, or yeah, actually everybody, will try to express it in a way that makes it easier for you to figure out what's connected to what. So, instead of saying CH4O, which would have been the most condensed way to write this, right? It was spelled out to you. It was expanded out as CH3OH to try to imply to you what's connected to what. So the way to read these things is just like you would a book from left to right. So what this says is that these 3 hydrogens are connected to the first carbon. So you have hydrogen, 3 hydrogens connects to the first carbon. And then there's an oxygen that connects to the carbon, right? And then the hydrogen is connected to the oxygen, okay? So that makes it easy, right? Whenever you see things are expanded out like that, use it to figure out the connectivity. And we still can do valence electrons here. That's 9, 10, that's 14. Okay. But now we have the skeleton, so it's nice. When I put in the single bonds, I've already used 10. So I got 4 left. Hydrogen doesn't need it. Let's put it 2 pairs on oxygen, right? So there it is. I've completed my structure. Okay. And now that wants a shape, right? How many central atoms do we have? We have a carbon and we have an oxygen. So again, we can make that table, right? Okay. Atom, carbon, electron group geometry, right? Count the electron groups around it. 1, 2, 3, 4. So that's tetrahedral. Okay. And what's the molecular shape? Well, it has no lone pair, so it's still tetrahedral. And then the bond angle is 109.5. For oxygen, 1, 2, 3, 4 electron groups, so it's tetrahedral as well. But it's got 2 lone pairs, right? So tetrahedral with 2 lone pairs. that makes bent, which is 105. Okay, so there we have it, right? Okay, so again, with the larger molecules, remember, you're going to do it one central atom at a time, okay? And again, whenever you have a chemical formula that is kind of expanded like this, kind of spelled out for you, okay, you'll know to just read it from left to right, right? These three hydrogens are connected to the previous atom, right? So these three hydrogens connected to carbon, okay? The oxygen is also connected to the carbon, right? Obviously, the oxygen is not attached to the hydrogen because hydrogen can only make one bond, right? So this oxygen has to be attached to the carbon. And then this hydrogen is attached to the oxygen, right? That's why it's written that way, so that you can work out the connectivity. Okay, okay. Let's go back to our slides. Okay, let's move on to molecular polarity. So molecular polarity has to do with whether a molecule is polar or not. And this is important in predicting whether your compound is soluble in certain things, how it's going to react. So it's really important to be able to determine molecular polarity. In the last chapter, we already determined bond polarity, if you guys remember, right? You can have, based on the difference in electronegativity, you could have nonpolar, right? Or polar bonds or ionic bond, right? This is related to that. But now we're considering whether the whole molecule is polar or not, and not just a single bond. Of course, the molecule is made up of many bonds. So what you actually end up doing is you do bond polarity for all of the bonds within the molecule, and then you assess them all together, right? And then you see if there's a net polarity or not. And then if there is a net polarity, then your molecule is polar, okay? So let's start with a really simple molecule where you just have one bond, so that it's really easy to assess, right? So if you have HCl as your molecule, HCl is a polar bond because chlorine is more polar than hydrogen. And or more electronegative, sorry. And so how do you know the electronegativity trend? Remember how it goes? Increases as you go to the right and up, right? So it increases diagonally to the right of the periodic table. So chlorine is to the right more than hydrogen, okay? And so chlorine is more electronegative. Okay? So what that means, right, is that chlorine draws electron density towards itself more than hydrogen, so that you basically have a partial negative charge on chlorine, okay? Because chlorine carries more electron density. So you actually draw delta. So remember what delta means: partial. Delta negative means the chlorine is partially negative, just because it has more electron density towards it, right? And now the hydrogen got electron density pulled away from it, so it's delta positive, right? It's like it lost a little bit of electron density, right? So this is what we call bond polarity, right? The HCl bond is a polar bond. And since it's the only bond in the molecule, then HCl, the molecule, is also polar, okay? So you have a polar molecule for HCl. Now, if you look at CO2, right? And if you draw CO2 with the correct three-dimensional shape, which would be linear, right? So draw linear, then you'll see that the CO bonds themselves are polar, but they are not, the whole molecule is not polar, because the bond polarity arrows cancel each other out. So let me show you how to draw polarity arrows so that you guys can assess the bond polarity. So when we had HCl earlier, right? Cl was delta negative, and H was delta positive. To draw the bond polarity arrow, the arrow head should point towards the more electronegative atom. And then you do this, right? You draw like a little butt of the arrow to say that it is positive towards the more electropositive. I think I showed you guys already in the previous chapter, but just as a review, right? So the arrowhead points towards the more electronegative atom, and then that positive butt towards the delta positive atom. So when you have CO2 and it's linear, right? Between carbon and oxygen, the arrow should point towards oxygen, right? Because oxygen is more electronegative than carbon. It's more to the right. Okay, so just look at your periodic table to determine that. And so the positive butt of the arrow should point towards carbon. Now, for this CO bond, I should have the arrowhead pointing like that. Okay. And so the butt of the arrow point again at carbon. And notice that this arrow is canceling this arrow out. Okay, so there's no net polarity. And so even though CO2 has polar bonds, the entire CO2 molecule is nonpolar. Whereas this, you do have net polarity, right? Here's the net polarity, is this arrow right here. So we have a polar molecule for HCl, but not a polar molecule, a non-polar molecule for CO2, even though CO2 has polar bonds, right? So not just because you have polar bonds does not mean that you are polar, right? You have to assess, basically doing addition of all of the arrows to see if there is a net polarity or not. Okay, let's do H2O. Okay, so for H2O, let's say if we, do the Lewis structure to begin with, right? We have 2 times 1 plus 6, that's 8 bits. We would put oxygen in the middle, and we would put the hydrogens on each side, okay? And then that's 4 electrons used, 4 are left, so we have 2 lone pairs on oxygen. Now, here's the limitation of Lewis structure. The way that, when you follow the steps and you got this, it is saying that, the way that you're drawing it, it looks linear, right? But we know H2O is not linear. What is this shape? Well, how many electron groups around oxygen? 1, 2, 3, 4. It's tetrahedral for the electron group geometry. Okay. But for the molecular shape, right? 2 lone pairs. So it's bent. Okay. So have to draw, in order to figure out polarity, you have to draw the molecule to the correct shape. So you basically have to draw it in 3D. So this is incorrect, right? It looks like it's linear. It's not. It should be bent. So really, water should be drawn like this. Right? So now we can correctly assess whether water is polar or not. Let's assess the OH bond. Polarity arrow should point towards oxygen. Right? In both cases. Okay. And now, to assess whether this is polar or not, think about, it's like a tug of war, right? Even in CO2, it was like a tug of war. Let's say that the flag is here, and we tie 2 ropes. One team's gonna pull that way, and we tie a rope to the other team, and they're gonna pull this way. Okay, so they're pulling opposite equal direction. The carbon, the flag, it's not gonna move. That's when you know that it's nonpolar. Okay, because you have no net polarity, right? The forces cancel each other. But here, what do you have? You tie the rope, one team's going that way, the other team's going this way. Okay, so the left and right direction is canceled, but there's a net motion of going up. So the oxygen will move up, right? If you have a team pulling this way, and a team pulling this way, the oxygen's going to move up. Okay. So let's say that water is polar. Okay, and here it really is the take-home message why you have to use 3D. If you'd done it on the 2D picture or the picture you just got from your Lewis structure, you would have incorrectly said that water is nonpolar, right? Because these arrow would cancel each other. So don't do that, right? Make sure you're using. So now I'm going to show you guys, right? The 3D, how to draw things in 3D. 3D templates for certain geometries. We're going to start with tetrahedral. Let's say, we have carbon in the center. And you have to draw, 4 things. It should look like that. Okay. So let me explain to you what those bonds mean. So if you are like this is in the plane of the board or your piece of paper. If you're like this, you're behind the board or your piece of paper. And if like this, you're in front. So it's trying to show perspective, right? So remember our tetrahedral? Okay. If I line this up in this way, let's line it up in this way. You see these bonds are in the plane. So they get just a line, right? But this bond here points to the back of the board. Okay. So this bond right here is the hatch bond. We call that the hash bond. And then the wedge bond, this bond is coming out at you, right? So that's the wedge bond. That's much better than this, right? You draw CH4, Lewis structure looks like that, looks flat. It looks like this angle is 90, okay? So that's deceiving, okay? It's not accurate. So I want you guys to be able, from now on, to draw CH4 like this. Okay. Now, doesn't that look better, like this angle? Is looking 109.5, right? Whereas the other one is looking 90. Okay. So tetrahedral and then trigonal pyramid is under tetrahedral, right? Trigonal pyramidal. That would be like, ammonia or something. So nitrogen in the middle, you replace sort of the bond with the lone pair, and it's still a hatch bond and a wedge bond. Okay. And let's step it up. We now have also trigonal, bipyramidal template. That's 5. So let's say something like phosphorus as your center. You're going to draw it like this. 3 lines, 1 in back, hatch bond, and then a wedge bond, 1 in front. Okay. Certainly, that's what it looks like, right? Okay. So if I turn it like this, like this, okay? These 3 bond, right? This one, and this one are the 3 lines, okay? And then this one pointing to the back is the hash. This one pointing to the front is the wedge, okay? Okay. So it's nice. You can say that we have 90 degrees here, and then this one is 120. You can actually kind of see that, right? So it's much more accurate representation. Underneath trigonal bipyramidal, there was a seesaw, right? Seesaw. So what that just means is you're still using trigonal bipyramidal template. You're just going to remove one of the bonds here and turn it into a lone pair. So if I remove this bond and rotate it down like this, then it's gonna look like that, right? Okay, and there we go. Okay, yeah, it's that be for seesaw. For octahedral, 6. So it's sulfur. You're just gonna do 1 up, 1 down, and then 2 hatch bonds and 2 wedge bonds. Okay. And square pyramidal falls under octahedral, right? Okay, you can do just take this one as take one away, this one as a lone pair. So there's lone pair, and then you still have 2 hatch bonds and 2 wedge bonds, right? Yeah. Yeah. So sort of the fatness that grows here is like the artist perspective of like a vanishing point, right? And so try to make it like that, right? Like make it skinniest first and then make it grow. Okay. For both your hatch and your wedge bond. All right. So now that you know the 3D templates, you can really accurately assess bond polarity, or sorry, molecular polarity, right? You draw the bond polarities on top and then on top of the 3D, and then assess together whether it's polar or not. Okay, so let's go back to board or the slides. I mean, so in order to assess molecular polarity, right? And one of the thing was the tug of war. I think that's a really good way to think about it, right? Just tie the ropes to where the arrows are and imagine in your mind, does the central atom move? If it doesn't move, then the forces cancel, right? And it's non-polar. If it moves, it's polar, okay? But what you're actually effectively doing is you're doing vector addition, okay? So here's a slide that shows you that. Let's say that both of your bond polarity arrows are pointing to the right. Well, obviously, that's going to be polar. They're not going to cancel, right? Because you're doing vector addition. To the right is +5, and there's another one that's to the right +5, that's +10. So the resulting arrow after you add is 10, okay? Now in example 2, you see you have a bond polarity arrow that's pointing to the left, so let's call that -5, right? Because it's pointing to the left. Then you have one that's pointing to the right, and it's longer, so let's call that +10. Well, if you add those together, you still have a net polarity because it's +5. So you'll, again, with the tug of war example, you got 2 teams A and B pulling opposite direction, but team B is stronger, so your resulting arrow is what? Things are going to move to the right, right? So you're going to be polar. Okay. In example 3, this was the CO2 example, right? You have left polarity arrow, so let's call that -5. Right polarity arrow is +5, -5 + 5 is 0. So the vectors cancel each other out. And that's why you have nonpolar, right, for CO2. So that's the only time when you have nonpolar is they completely cancel, okay? Now, examples 4 and 5, those are just interesting. Like, let's say that you don't have, if you have vectors that are, diagonal, then what you do is you line up their butts, and then you draw a parallelogram. The diagonal is the resultant of A plus B. So pretty cool way to do vector addition. But you really don't need to do that, right? You can visually see it, and especially if you imagine, tug of war, you can correctly assess. So what ends up happening is, right, all the really symmetrical molecules are going to be nonpolar. Symmetrical as in the shape is symmetrical, so linear, trigonal planar, tetrahedral, those are all really symmetrical, right? But also the surrounding atoms have to all be the same as well, okay? Because if the surrounding atoms are not the same, then you're gonna have a polarity, right? And then all of your other, like your bent, your trigonal pyramidal, basically anything, most things with lone pairs are gonna be polar, right? With the exception of square planar, because the lone pairs are opposite of each other, so they cancel, okay? But yeah, you can kind of generalize it, right? If you see a really symmetrical geometries with all of the same surrounding atoms, that's going to be nonpolar. Okay. So yeah, let me show you an example here. All right. So the difference between, let's say if I have CF4, okay, to quickly draw the Lewis structure, right? We know it's fluorine, it's tetrahedral, because carbon's making 4 bonds. So make sure you draw it in 3D, okay? This is going to have 3 lone pairs. So now we draw bond polarity arrows between carbon and fluorine. Which one is more electronegative? It's the fluorine, okay? So draw it, bond polarity or arrows towards fluorine, right? And each time just draw it parallel to the bonds, right? That's why it's nice to draw it right on top of your 3D Lewis structure, just so you can see. So all the arrows, as you can see, are pointing in opposite direction, and they're equal, right? Because it's the same atom. So this is clearly nonpolar. And this was an example that we were saying, if your geometry, which is tetrahedral, right? It's really symmetrical, and all of the surrounding atoms are the same, then you're nonpolar. Okay? But what if you're CH2N? Then you're like this. Okay, so what does that mean? By the way, CH bonds are nonpolar. So whenever you see CH bonds, I mean, obviously CC bonds are nonpolar, right? Because it's the same atom. Anytime you have same atom, it's nonpolar. But CH, there's so little difference in electronegativity. I think it's like 0.4 or even less. Remember, if it's less than 0.4, it's nonpolar. So you don't need to draw bond polarity arrows on top of CH bonds, right? That makes it easy to assess now. You got 2 arrows going that way, your net is that way, right? If you have 2 teams and they're both pulling this way, that carbon is going to go that way. Okay, so we are polar. Right? So why am I showing you these 2 examples? Just because both are tetrahedral does not mean that they are nonpolar. Both are tetrahedral, but only this one is nonpolar because all the atoms are the same. Okay, so you gotta be careful about that. So that's why I would not memorize which geometry is nonpolar or polar. It's kind of useless, right? It depends on case by case. Really, the best thing you need to do is just redraw once you get the Lewis structure, and if you'd done Lewis structure here, it would have looked like this. Right? And so and that would be wrong to just leave it like that, because that's square planar, right? The way that it's written. So you need to convert this to 3D before you put the polarity arrows on top. Okay, it's very important. Okay, same thing here, right? Let's say that you've drawn CH2F2 like that, and then you put polarity arrows on it. You don't do it for CH. You would have said this one is nonpolar. See, it's dangerous. Do not do it on your Lewis structure. Do it after you converted your Lewis structure into 3D, and you will not have this problem, right? Because it is actually polar. Okay. So redraw it in tetrahedral. You know the template now, right? You can say, okay, 1, 2, 3, 4 electron groups is tetrahedral. So I should use my tetrahedral template and then do the bond polarity arrows on top, and then assess whether the whole entire molecule is polar or not, right? Okay, so let's do this as a last example. Determine whether NH3 is polar. Okay, so from the very top, we start with a chemical formula and then go all the way through. Okay, so NH3 First step, Lewis structure, okay? And even take notes here, right? Step one, you draw the Lewis structure. 5 plus 3 times 1 is 8 valence electron. Nitrogen is the central. H spread evenly. Single bonds only. That's 6 electrons used, 2 electrons left. The hydrogens don't need the electrons, right? So we put the 2 electrons or 1 lone pair on the nitrogen. Okay. Octet is fulfilled, right? Formal charge, let's do it for nitrogen. 1, 2, 3, 4, 5. And it should have 5, so that's 0. Hydrogen 1, so it should have 0. So check formal charge. Okay, that's our structure. Now look at the central atom. Remember, when you're doing shapes, all you worry about, all you need to do is do the central atom. So 1, 2, 3, 4 electron groups around nitrogen. So electron group geometry is tetrahedral. Okay. And molecular shape, right? 1 lone pair, tetrahedral with 1 lone pair, trigonal pyramid. Trigonal pyramid. Okay. Once I know the shape, right, I redraw it in 3D. Convert it to 3D. Remember the trigonal pyramidal template? Actually, you can even do it off of the tetrahedral template, right? Just go, okay, I know the tetrahedral template is that, but one of my bonds is a lone pair, so I just erase it, put lone pair, and then I put my hydrogens everywhere. Okay, and that's my 3D. Okay, so what did we do? Let's take notes here of our steps. Draw a Lewis structure first, then determine electron group geometry and molecular shape. Of the central atom. Okay. In step 3, you're going to redraw. Very important here. Redraw structure in 3D. Okay. Use the templates that I showed you guys. And then step 4, we are going to put bond polarity arrows on top of each bond. It's an NH bond. Which atom is more electronegative? Nitrogen. Nitrogen. Now we assess. Do these arrows cancel each other out, or is there a net direction? They're all the lateral direction, right? The left and right cancels out because they all push this way. However, all of them are what? Pointing up. Okay. And so that's our net. Okay. Or you can imagine, right? 3 teams. And they're all pulling that way. Okay, so the nitrogen's going to move up. So yes, NH3 is polar. And again, right? Remember what I said? Trigonal pyramidal. Those are usually polar because you have a lone pair. Okay. And it's asymmetrical, right? This looks asymmetrical because there's nothing up there. Right. So asymmetrical geometries usually led to polar, right? Even when these atoms are the same, you know, because it's all going that way. All right, so take notes there. Number 4, what do we do? Draw bond polarity arrows. For each bond. Draw bond polarity arrows for each bond. And then assess whether there is a net polarity. So if there's yes, is polar. No, it's not polar. Okay, so there's a net polarity, right? The central atom moves, polar. If the arrows cancel each other out. Yeah, so that's it, guys, for this first lecture. I'll see you guys next time. for the second lecture video.